Log on, tune in, find out. Another good idea from Cambridge.
Begin by thanking the organizers of all of this program for having me here. It's very nice to be here in Cambridge during the spring, and also for allowing me to give this talk. So this is the title, Multilinear Kakeya type inequalities and factorization. So actually Frank asked me for a title, and I was just going to the city center, and so I was sent this title in by my mobile phone. So maybe, if I'd had a moment's thought, I would probably have checked the spelling, and then if I'd sort of considered the content, then maybe it's more appropriate to say multilinear Braskamp-Leib type inequalities and factorization. But we'll see that maybe it's not essential in what I want to talk about. I mean, it applies to sort of both, but we have more examples on the Braskamp-Leib side. So also I would like to point out that what I'm talking about is joint work with Anthony Carberry from Edinburgh, and who's in the audience today. Okay, so this is sort of just a little question in the beginning, something which you will be able to answer. So I'm going to start off with, we have a function. Let's just take a positive function. But I might just as well say now that almost everything I will be talking about are positive valued. So I won't explicitly say it at every point, but just in the beginning, and then think of everything as being positive. Otherwise, there should be absolute values for some things. So we have a positive function m, and let's say it's in L2, and it's on two-dimensional space. So which two-dimensional space doesn't really matter. It could be R2 or the integers, the integer lattice, two-dimensional, or it could be some finite lattice. So let's say a finite field with q elements, and then the vector space of dimension 2 over that. And just to make things sort of normalized, we'll just assume that the M has L2 norm, which is 1. And then we have this factorization result, which is that we can find two functions, but they're both of two variables. So maybe this is not so impressive that I can factor a single function of two variables into the product of two functions of two variables, and they have the square root. So this is not maybe the product. We could also say this is a geometric mean. So with the square root, it's a geometric mean of these two functions here. But the point is that these two functions are sort of have quite sort of orthogonal properties. I mean, so one of them you have that if you integrate one of them, so s with respect to y, then for every x, this will be less than 1. And the other way around, if you integrate t with respect to x, then for every y, this will be less than 1. The 1 here is the same as the 1 there. So I want to explain how this sort of thing comes about. I think this is quite sort of striking. And it follows from this very nice inequality, which says that if you have two functions of one variable each, so f of x times g of y, and you integrate this product, then this is less than the integral of f of x times the integral of g of, so f of x over x and the integral of g of y over y. And now some of you might say that this should not be an inequality. Of course, this is an equality, and it goes by the name of Fubini's theorem. Although when I learned it at university, it was called Tonelli's theorem, because everything is positive here, and I don't know if that's something you've heard as well. Okay, so this is sort of, a brief preview of what's going to happen today. And so I have this slide here, which is as a very sort of high-level outline of what I'm going to talk about. So there's absolutely no mathematical content on this slide, but it sets the sort of, it explains the story I'm going to tell you without any mathematics. So I'm going to try and present a little bit of a background for sort of where this comes from. And I want to try and give some arguments. I mean, the arguments I'm going to give are quite simple, I think. So I feel like I should be able to present them. And therefore, I want to sort of review a piece of argument from the literature. Of course, I will tell you who it's by in a moment. But I will just do it in quite a simple case, so where everything is sort of nice and discrete. And then we will think about, so how can we reverse the implication which this argument has. We will try and discuss a little bit. So I will start off talking about in this model case, and then we'll move on to the general case and write down some consequences of the general case. and just a little bit sort of a flavor of what happens when we have to actually write down the argument for the general case. So what are the differences from the model case to the general case? So this is just sort of a high-level outline of what I want to talk about. Okay, so background. So where are we coming from? I suppose a question mark would be in order there. So there are sort of maybe two sides to that, but it's also quite closely related. So again, I managed to almost do this without any mathematics. So there is this notion of the Kakeya conjecture, which has sort of been very central in harmonic analysis for a number of decades now. So this has something to do with how you can fit a line segment in every direction in a small set, or how small that set can be. I mean, it's not essential for what I'm going to talk about precisely the statement, but this is just where it's coming from. So don't worry if it's, I mean, if you've heard about it, sure. Otherwise, don't worry. And we can sort of phrase this, well, this conjecture has sort of different degrees of difficulty. We can talk about the dimension of things, or we can express it as an Kakeya inequality, and which is one of the stronger form of this conjecture. But all of these are conjectures at the moment, so there haven't been any. I mean, there have been progress, but no, it's not done. So people have sort of been trying to attack this from various sort of different viewpoints, trying to get closer to the results. And so one of the methods of attack, we could say, is instead of considering this Kakeya inequality, is going to a sort of a multilinear Kakeya inequality. And this was originally introduced by Bennett, Carberry, and Tao. And they sort of proved this multilinear Kakeya inequality. I mean, the original Kakeya inequality doesn't follow. And moreover, I mean, in their proof there is also, it's not the complete result even for the multilinear inequality, because it sort of misses an endpoint. So what happened after that? Well, there are sort of what's relevant for this talk is first of all that on so this conjecture originally talks about sort of sets which live in Euclidean space, but you can model maybe this setting with a question which lives on vector space over a finite field. And in that setting, actually, the Kakeya conjecture is not a conjecture, it's actually a theorem, which was proven by Dvir. And he introduced the polynomial method, sort of looking at zero sets of polynomials, introduced that very sort of neatly into this problem and gave a very elegant proof of the results of the Kakeya conjecture on finite fields. And the thing is that this polynomial method has sort of been adapted to the Euclidean space by Guth. Well, again, looking at zero sets of polynomials, but sort of we're not fixing the zero at a particular point, but we're sort of using algebraic topology to understand the set of zeros and where that can lie. And it also Guth doesn't prove the Kakeya conjecture. The result is about the multilinear Kakeya inequality. So he gets sort of the endpoint of that inequality. So that inequality is completely settled in the Euclidean case. So this proof of Guth is sort of the starting point of what I'm going to talk about. It's sort of I take a piece of that proof and sort of do something with it. So this is really the starting point of what I want to talk about. So the other angle where we can also look at this as coming from are the Braskamp-Lieb inequalities, or the Braskamp-Lieb inequality. So it's a little bit related. So you can sort of view the multilinear Kakeya inequality as a sort of a more complicated version of one of these inequalities. But let me just talk about what the Braskamp-Lieb inequality is. Of course, many people in the room know them very well. So what we have here on the left-hand side is that we have we're multiplying together some functions, fj, and the functions fj, they live on this small space R and j. And to be able to do this, we have to go from the big space Rn to the small space. So we just have linear projections, Bj, which map the big space Rn into the small space Rnj. So then you can evaluate these functions. You can multiply them together. We raise them to these appropriate powers, and we integrate this over the whole space. So these powers are non-negative real numbers. And on the left-hand side, there is some sort of interaction between these functions. I mean, you're multiplying together pointwise these functions, whereas on the right-hand side, there is no interaction between the functions. You just have the integral of the functions sort of by itself, each function by itself, and then you sort of multiply together everything at the end. So there's no interaction somehow between the functions on the right-hand side. And this, so this inequality may or may not hold, and I mean, with a finite constant. Of course, if C here is infinity, then of course it holds, but it's not very interesting. It's a bit vacuous. So whether it holds or not depends on actually these linear transformations and these powers. So the relationship between the linear transformations and the powers. So this inequality is quite general. So it sort of generalizes several quite well-known inequalities from an analysis, and maybe the simplest one is just when Rn is equal to Rnj, and this space is just the same, and there are no linear transformation, if you like, and then this is just multiplying together functions which live on the same space, all of them, and then if the exponents add up to 1, you have the multilinear Hölder's inequality. And here is the another sort of example from geometric analysis, if you like. So this is the Loomis-Whitney inequality, and I sort of wrote it up in the smallest case, which I thought was vaguely interesting, which is on 3 dimensions. So you have now 3 functions, and the projections here, the linear transformations are projections which forget one variable. So the first projection forgets the x variable, the second forgets the y variable, and the third forgets the z variable. So you multiply, and then you have these functions of 2 variables, f, g, and h, which you evaluate at these points. You put the appropriate power, which is 1/2, 1 over the dimension minus 1, and then you have the Loomis-Whitney inequality. So this is sort of maybe the first case, the 3-dimensional case is maybe the first interesting case, but there of course is a 2-dimensional case, which is this very strange inequality I wrote before, which is not an inequality at all, it's an equality, which is Fubini's theorem. And maybe the final, one more example is sort of, which is a little bit the reason for why this Braskamp-Lieb inequality got sort of written down by Braskamp and Lieb. So this is the Young's convolution inequality. I just wrote it down in a special case where the powers here, it's enough that the powers just add up to 2 and that they're all less than 1. Then you're integrating sort of f of x times g of y minus x. So you evaluate f at x, g at y minus x, and h at y, and you have this product, and you get this estimate. And the point is that Beckner proved that this constant is not just 1, which is you can get very easily by interpolation, but it's actually less than 1. And then Braskamp and Lieb sort of studied that a bit, that question further. Okay. So what I want to talk about, this model case I want to talk about, is sort of Loomis-Whitney inequality on a finite field. So the point is that on a finite field, everything is discrete. I mean, you can make sort of various discretizations, but on the finite field, it's complete. I mean, everything you talk about is discrete. And I want to talk about Loomis-Whitney inequality, but maybe I wrote it in a little bit strange way. So I just want to sort of emphasize what it is. So I have this nice picture of maybe not the absolutely simplest case, but not far from it. So I have a finite field with 3 elements, 2-dimensional vector space over that field. And then Loomis-Whitney, I was saying before, it talked about functions which did not depend on one of the variables. So it forgot one of the variables. So if they don't, so for example, if they don't depend on, let's say, the x variable, then they will be constant functions on these blue lines, on each of these blue lines. So we can sort of say that these are functions which are functions really of the lines. So we have a collection of, and again, if they don't depend on the y variable, then they will be constant on each of the red lines. So we can say that they really are functions defined on a line. So to each line, we have a value. So the domain of these functions are the lines, and for each line, we have a value. And so this is the inequality, Loomis-Whitney inequality. So you integrate over the finite field, you multiply together these d functions. I already said that the power here was 1 over the dimension minus 1, which is 1 over d minus 1 in this case. And so instead of having sort of talking about functions which forget one variable, I will just say that they're actually defined on a set of lines. So the point is that that within each collection within each of these collections, all of the lines here are in this collection are parallel, and all of the lines in this collection are parallel, and they point sort of the directions of these, one from this collection, one from this collection will span. So that's a general situation. You have a collection of lines, and if you take one line from each, so within a collection all of the lines are parallel. If you take one line from each collection, you get the direction of these will form a basis for the field. Now the only sort of additional remark at this stage is this sum here is a little bit strange. For each point x, well, I fixed j now, I'm taking the line, the sum over all of the lines which x goes through in this collection. Of course, if the lines are all parallel, there will only be one element in this sum. But I have a sum here, so if there's a sum, it actually looks a bit more like the multilinear Kakeya situation. There we could sort of relax the condition that all of the lines have to be parallel, just have a condition that the lines should sort of point in different directions, roughly. But of course, but I'm going to have a sum here because I want to interchange two sums later on, and if I don't have two sums, I can't interchange them. So it'll be the same. Maybe this sum has only one element, but after I interchange them, I will anyway get two sums. So I just had it like this. So this is the left-hand side where we have sort of an interaction between these mu's from different collections. But on the right-hand side, we just have from each collection, we just sum over the coefficients and then multiply them all together, these sums, and raise them to the appropriate power. So this is the inequality I want to talk about. So I want to just outline how Guth's argument deals with sort of his first part of the argument. So they're really, so I want to talk about Guth's proof strategy. And there are sort of two parts of the argument. So one of them is just a very simple reduction, which is a bit strange, and this is what I want to show you. And then the other part is to establish this thing here. So what the Guth argument goes like this. He has this inequality. He reduces, instead of proving this inequality, he says that he demonstrates that it's enough to prove a statement like this. So what is this statement? So we're given a function m, again positive. Let me not say that all of the time. It's defined on this vector space, d-dimensional vector space, and we want to find functions, so d functions, which are defined on the same vector space, and again positive, and they should be the following. So the geometric mean of these functions sj should dominate the original function m. So this, of course, these sj's have to be a little bit big, but they should not be terribly big. They have this property that if you sum, so sj, if you sum over any line from the jth collection, then this sum should be less than this number here, which is the d norm of m times this power kd, which is the same, I want to say the same power as appears in the inequality, but there's actually it's actually to this power. So just change the power here because I prefer to have no power on this side. I could, of course, move it to the other side, but I prefer to have the power here, and then this is actually what you need. So there is something which says that the st should be large, and there's something which says that it should not be too large. And you can sort of move the problems around. So, I mean, because this sj only has to worry about the direct lines which go in the jth direction. This is somehow the benefit. So how do you actually go from this, or let's say from this to this? And it's very simple. And let me just demonstrate it. So this slide, and so I'm going to try and go through and just quite slowly. So you start off with, so this was what you started off with originally. And we just take it upon ourselves to define a function m, which is so that this expression here in red is equals m of x to the d. This is just the definition of our function m. And but the next step, well, okay, I mean, sure, we can of course define this. I mean, m will just look like this, sure. It's just to split m to the power of d into two terms, one with the power 1 and one with the power d minus 1, of course, yes. And and on this term, you so for this term here, m of x, we use that m of x is dominated by the geometric mean of these sj's. So we replace this m of x to this square by this geometric mean. And this d minus 1, m of x to the d minus 1, we actually just look at the definition of m again and realize that once you have the power d minus 1, they actually switch sides. So here we had 1 over d minus 1 and d. So if we actually have the power d minus 1, then we have 1 over d. So they just switch. And then you just notice that actually this, if you think about it, this term here is now a sum, or in general, I mean, it would be an integral of the product of two things. Well, if we can multiply them together, and then they're the product of d things. We can take one term each from these, join them together, and then there we have d terms in this product, and the power is 1 over d. So it makes sense now, of course, 1 over d times gives you 1. So now it fits to use multilinear Hölder to pull this product outside. So we use the multilinear Hölder's inequality, which I talked about before, to pull the product outside of the sum. Of course, the power moves over there as you do it. And now we have this this term here inside, and this is a double sum, which I sort of alluded to before. And once we have this double sum, what we want to do is we want to interchange the sums. So even if I didn't have any sum here, so if I was actually had just written this down sort of more, which look like the Braskamp-Lieb inequality, I would still have two sums on this side. The only difference after I've interchanged these sums here is now the shape of the argument looks exactly the same whether I have the Braskamp-Lieb or the multilinear Kakeya sort of type inequality. The only question is, are all of these lines in each collection, are they all parallel or are they all just roughly parallel? So so we have this situation, and of course interchanging these two sums, if you look ahead and for the general case, it's sort of going from a operator to the dual operator, but we'll sort of see that later when we talk about the general case. So what happens next is that we just now recall the second condition on our lines. So the sum over sj's over these lines was actually supposed to be less than this number here, and it's to the power 1 over d, but there are d terms like this, so you actually get kt, the dth norm of m times this term here. And now you just rearrange, so this dth norm here is actually just the power of this expression here. So you collect these together and you end up with what you wanted. So this is how the proof goes. It's just a very simple reduction, but maybe it's not quite obvious that you should want to do it in the beginning. But it's quite sort of neat. So you end up with this expression here. These are two sort of powers of one another, and you collect them. So this is actually the problem which you then have to deal with. So Guthrie has reduced the problem to dealing with this situation here. And that's where he starts talking about, so the definition when he's in the Euclidean space, the definition of these sj's comes about by studying these, it's the algebraic topology he starts to enter, and it sort of talks about, creating certain polynomials, or proving the existence of certain polynomials, and then these sj's will have something to do with how the zero set of these polynomials will intersect cubes, sort of very, very roughly. But can you sort of look at this and do something else? And one thing you can observe just if you take a look at this is that this is actually, you can think of this as an optimization problem. I mean, we can think of this as, what is the smallest k? So let's say we're given m, we're given our input m, what is the smallest k so that this holds? So what we would really like to have happen is that this k actually should not depend on m at all. Then we would be really happy if we could make this k be independent of the function m. And but for a given m, then this is sort of an optimization problem, right? The input is m, which enters here and here, and then we have sort of things which you can play around with. So we can play around with these sj of x, and then this constant k, which you would like to be able to go down. I mean, you can see that if k was allowed to be very large, because there are just we could just fix k massively huge, and this would be okay. But the point is, how small can we make k? And if you take a close look at it, then this is actually a convex optimization problem. So it's convex, so the variables are the k and the sj of x. So the value of the function sj at each point x are the variables. So maybe I'll just put that up before. This is a number of variables, just to make it clear. K is 1. We have d functions, so that's a d here. And for each of these functions, we have to decide on the value of this function at each point of the field of the vector space, and the vector space is q to the d. So these are the number of variables. So it's linear. This is linear. This is linear in k completely, and this is linear in the variables. And this one is so the geometric mean of functions is concave, but we should actually move it to the other side. Then it gets a negative sign, and it becomes convex. So that's exactly the definition of a convex optimization problem. It's allowed to have constraints, which are inequality constraints, which say that a convex function is supposed to be less than 0. So that exactly fits convex optimization. So if you see a convex optimization problem, I think maybe the most obvious thing to think about is, what does duality theory say about this problem? Or does it say anything at all? And let's just see what happens if we try and do duality theory. And the point is, for why I'm having all of this on the finite field is because then we both have a finite number of variables, and we also have a finite number of constraints. So the number of lines in this finite field will be finite. So this would be extremely sort of straightforward to write down what duality theory says about this. So we write down the Lagrangian. So what is a Lagrangian? I mean, this is of course quite standard, I guess. If you're interested in this type of stuff, you just have the function you're trying to optimize, which is k, and then you add onto it so each of your constraint functions, and you multiply each of the constraint by a Lagrange multiplier, I suppose, or something which will become a Lagrange multiplier in the end. So for now, for us, it's very convenient to write these as a function, because this will be, there's one Lagrange multiplier for each point in the vector space, so that will be this g of x, and there is one Lagrange multiplier for each line, and that will be this lambda. Okay. So, and then we want to sort of try and figure out, so duality theory says we should try and we should define a dual function h of these new variables g and the lambdas, and which should be the infimum of the Lagrangian over these original variables k and sj. So let's try and figure out, and then afterwards we want to try and maximize the dual function. So the maximum of the dual function will be closely related to the minimum of the original stuff we were trying to do. It'll be the same. But of course, the maximum of this function, or the supremum of this function, I should say, we will not expect to find that at the places where this function takes the value negative infinity. So let's just try and exclude the places where this function takes the value negative infinity. We shouldn't look for our supremum there. So let's just try and simplify it by doing that. So to do that, I'm going to try and figure out when this function takes the value of negative infinity. I'm going to, of course, now the point is that I can play around with these k and sj's to try and make the function be small, go to negative infinity. So let's try and rearrange this stuff just to sort of pull out the action of k and the action of sj sort of separately. Let's try and separate that out. So this is just a rearrangement of what I had before, multiplied out a couple of terms and rearrange them. So let's immediately look at what the k variable does. It multiplies this expression here. So k is actually, at this stage, it's actually allowed to be both positive and negative, although really on the positive side is only the one which matters, but it's allowed to be both. And if you see it's allowed to be both, then well, this term will definitely just have to be 0. Because if this term in the brackets is not 0, then if it's positive, we can just make k negative and let k be very large, and this becomes negative infinity, and the other way around. If this term is negative, then you can just take a positive k, which is very large, and the L will become negative infinity. So in fact, this we have to deduce that this has to be there has to be equality here. So this term in the brackets has to be 0, and if it is 0, well then I can just skip it, right? So the SJs are maybe just a tiny bit more complicated. So well, the problem is that we have sum of SJs here and the product of SJs there, but we just relate the sum term to a product term using the arithmetic geometric mean inequality, and so we relate the sum over the SJs to this product. Of course, the arithmetic mean should have 1 over d, so just move the d over here, and the coefficients also get the power there. So we see that this term will always be larger than this term. And now if we look at, in both, now we have here and also here, we have this geometric mean of the SJs, but the coefficients are, it's this, and then it's this. So you see, if this coefficient is larger than this coefficient, then there is no way of fixing up some SJs to make this L go to negative infinity. There's nothing you can do, because it's clear that there will always be a positive contribution from these terms here, because this stuff here will be greater than this, which again will be greater than this, provided that G is less than this. So then there's no way of making this L be. If this inequality holds, there's no way of making L go to negative infinity. But on the other hand, conversely, if this inequality here does not hold, then we can play around with the coefficients, Sj, and actually make things go bad, maybe make it go down to negative infinity. So it actually turns out that this condition is actually also a necessary condition. But once we have that, so we're trying to think about how, because the dual function takes the infimum of L here, so how can we then make this expression small? And if this condition holds, actually the best thing we could do, or I should say, we can do no better than just taking SJs all equal 0. So this term will actually have no contribution. So in that case, we can just drop it as well. So the dual function will in that case be this. And now the point is we want to try and maximize the dual function. So we're looking to maximize this dual function, which is this thing here, but the conditions we have is this and that thing there. So of course we have sort of several variables. We both have the lambdas and the g's going on in this dual formulation, but we can get rid of the g's quite easily, because you notice that this expression, we're trying to maximize this expression. So if you're trying to maximize this expression, the question is how do we choose g? Well, it would be good to choose g large. So you just look at the condition here, and it turns out that g large, the largest you can make g is to be this, so you just substitute this in, and then there is no g appearing in the problem. Well, it appears in this constraint, but it's now irrelevant. So actually the dual problem only has this constraint, and we're trying to maximize this. So this is the dual problem. We're trying to maximize this expression subject to this single constraint here. And now the question is, we want to try and figure out, how big can this maximum be? It is a maximum because everything is finite. Don't have to say the supremum. So how big can this maximum be? So let's just try and think about it. Let's look at this expression and see how large, whether we can find an upper bound for it. And we can. So how do we find an upper bound for it? We just so this is again now, let's say a sum, but let's say an integral, where we have the product of two things. So we already know that the d norm of m was supposed to be a little bit important for us. So it's natural just to try and use Hölder, pull out the d norm of m, and then the conjugate of d is d over d minus 1. So you have d minus 1 over d here, and this, if you multiply the power with this, it actually, the power here turns into this power when you multiply it by the exponent. But the thing is that, that this expression starts now to look eerily familiar. This is actually the left-hand side of the expression we started off with, integrating over the space and the product of these expressions here to this power. This is exactly the inequality we started off with. So if we know that, so what did that inequality say? It said that this expression, I mean, if you assume that we know this inequality, right? So I'm sort of going the other way around now. Certainly here I'm using the reverse of the argument. I'm not going to assume that this inequality holds with this constant which you had before. This is just the same expression you had before. If it does, then we get this, which you can then just rearrange. It didn't really do anything here, just simplified, pulled this power inside of the brackets. And then we have this product of these things. Well, but the product of this to the power 1 over d, we can estimate by, this is the geometric mean, and we can estimate this geometric mean by the arithmetic mean, and we get this expression here. And now if we just look at the, so all in all, we've determined that this expression here is less than this one. And if you just take a look at, so I've just rewritten those things in red. This is what we had determined. But we're trying to maximize this quantity here, subject to this constraint. But of course, so this is the quantity. There's a d missing. Well, there's a d 1 over d here. And the on the right-hand side, we just have exactly this expression, which already the constraints already told us that this was 1. So we determined that the maximum of this problem is less than k, d. And so then the strong duality, which holds, so there's always a condition to check whether if, you know, in duality theory, you have to check some sort of extra condition to see whether the duality is true. And there is something called the Slater's condition, and it's very straightforward to verify that it's true in this case. So we see that a strong duality gives us that there is a solution to this problem here. So let me now just try and summarize what we've been doing. We've determined that there is an equivalence here. So on the right-hand side, we have this Loomis-Whitney inequality, if you like, and on the left-hand side, we have this factorization property. So we determined that these problems, so the going to the right implication is what Guth had, and we've sort of reversed it into the left implication with the arrow going to the left. So that's the equivalence we've established. Okay, so I now want to try and explain what the general version of this is. I mean, the simple version is I wrote up is just because I could really go through the whole argument in the simple version. You know, the general version is a little bit more technical, but let's just see what happens. So there are a lot of things going on the slides, but I have several colors to compensate. So, so before we had vector space over a finite field, and now we just have some measure space x. So x is now just a measure space with measure d mu. So of course, instead of having the sum over this measure over the vector space, I now just have the integral with respect to the measure. So the integral over x with respect to the measure. And similarly, these lines. So before we had something, you know, we had these mu's which were defined on the set of lines, but instead of that now we just have functions which are defined on some, again, new measure space y. So the correspondence is that in our previous example, yj was the set of lines from the jth collection. And that again appears here. So the next point is that instead of having on this side, so, well, we started off here with mu is a, so the mu's were functions sort of defined on the set of lines, and we wanted to turn them into functions which were defined on the vector space. So what was how did we proceed? By going from the lines to the vector space, we just summed over all of the lines. So for, you know, if we wanted to evaluate this new function at a point in our vector space, what we did is that we summed our old function over all of the lines which went through this point in the vector space. But of course, this is just some, we replace this now just by a general linear operator. And let's say it's positive. So to make things nice, so we want to say that this is a positive linear operator. So it takes this positive function or non-negative function fj, which was defined on the small space yj, and somehow cooks up a function tj of fj, which is defined on the big space x. So before, this was just summation over all of the lines going through a point. And we now also have the tj star operator, which is when we were handed a function on the big space, and we're supposed to return a function on the small space. And what we do is that, this sum here, for each line, we sum over the points x in the big space which belong to this line. So that's what the tj star is. You can just easily check that these are, if you define tj as this, then tj star will obviously be this. So instead of having now, before we had here an integral, or the sum, we replaced this by a pj norm, and then of course the soup which appeared here has been replaced by a pj primed norm. So this would be an L1 norm, which is an L infinity, so there's conjugate indices there. And one more expression we talk about is the powers. So before we had this power here, which was just 1 over d minus 1, but it could actually just be any power rj greater than 0. It doesn't have to be greater than 1, it's just greater than 0. Of course, it would be very bad if it had to be greater than 1, just greater than 0. And it could even be different powers for different terms in this product. So here, for every j, this is the same power, but it might be different. So rj could actually depend on the j. And then we sum up these powers rj to give us this power r, and r actually has to be greater than 1, which it is in the model case, because if you sum this power over all of the terms in this product, which is d terms, then we get d over d minus 1, which is greater than 1. So we're fine with this. And then at various points, we have the LR primed norm appears. Well, d over d minus 1, I was just saying, was the power r, and then d is the conjugate power to that. And then we have this, instead of having a function m in LD, we have a function m in LR prime, which is here. So this is how we construct the general version from this.
There is no condition between the pj's and the rj's.
No. Right, yes, that's exactly right. There are no conditions. These are all the conditions we need. Yeah. So we just, so I should just maybe, I mean, in the end, we just have this, the multilinear inequality. We just now have these linear functions. So maybe I should say, I mean, maybe you don't like to call this a multilinear inequality. If you're very picky, of course, it's not linear in any of the variables at this stage. I mean, if I take fj and another, fj tilde and add them together, and then, well, tj is linear, so that's fine, but then I put this power rj here. So it's not quite multilinear, but I'm going to continue calling it multilinear because I think there's no other good option. But there is this sort of form, which is not quite multilinear, but, you have this linear operator multiplied to the power rj, multiply all of these things together, integrate them, and this is, so the multilinear inequality says that this is bounded by the pj norms of the functions to the power rj, and the factorization inequality says that for any m, which is in this LR primed, you can dominate it, or, I mean, there could be an equality here, that would be fine. You can dominate it, or say it's equal to, and now this is sort of not, I mean, should I say it's a geometric mean? I can at least say it's a generalized geometric mean. It's a weighted geometric mean. The weights are the powers here, and the weights sum up to 1 because rj sum up to 1. So there's a weighted geometric mean here, and so this means that the sj have to be quite big, but they're not very big because if you apply tj star to sj, then this is bounded in this pj primed norm by this quantity here. Okay. So how does this actually, so let's just try and see how this comes out in some cases. So for example, in the Braskamp-Leib inequality, so this is now the general Braskamp-Leib inequality. So I want to just be slightly more, I mean, we can always make this happen. So I had Rn and Rnj, but we can just fix it so that Rn is actually some Hilbert space X of n dimensions, and Rnj actually is just some space Yj of nj dimensions, so of dimension nj, which sits somewhere inside of Yj. We can always make this happen just by some identifications, and we can also assume that the Bj's are projections. If they're not, we can just compose them. We can make general functions out of a projection and something, and then just move these things around. So this is not really any restriction. This is just a notational convenience. So we have a Braskamp-Lieb inequality on this side. We assume that it holds. So we're giving this Braskamp-Lieb data, so the Bj's and the powers Rj, and we have this inequality here. And then what are these operators, which we talked about in the operators here are now the Tj, which is supposed to take functions on the small space and give me functions on the big space. It actually takes a point in the big space, throws it down with this projection, and evaluates a function at the result of the projection. And then the dual of that operator takes functions on the big space, puts them on the small space, and how does it do it? It actually integrates out any dependence in the perpendicular plane or the perpendicular space. So I need projection for this actually to be exactly true. So it's notation. So I can integrate over the perpendicular space to the Yj space, and then just for any y in the Yj, I integrate over the whole perpendicular set. Okay, so that gives me what Tj star of S is, and then I've just put that here. This was supposed to be the Tj star of Sj here, and also now how are the powers? The powers here, before I had this Pj, but now in the Braskamp-Lieb inequality the Pj is 1 for each j, and therefore the Pj primed is infinity. So it's actually, this should really be the soup overall y. So if I change y it says for every y, this integral here is less than this number here. And then the Braskamp-Lieb constant, which we have an expression for, provided that you know what the datum is, and you have an expression for the Braskamp-Lieb constant, this is k to the r, and it features here as, you take the rth root of it, so it's there. Okay, so what are the sort of, this is a general case, so what is the sort of, so this is the Braskamp-Lieb factorization principle now we have for any Braskamp-Lieb data, for any function m, we have this principle here that we can construct this function Sj with these two properties. So this is a general situation, but let's look at some particular cases. So the case, so Fubini is this is what I had on my first slide, and this is what it says, that you can factor these any L2 functions, let's just say on R2, which has normalized to L2 norm 1. You can factorize it as a geometric mean of two functions such that you integrate one of them with respect to y, then for every x this is less than 1, you integrate the other with respect to x, then for every y this is less than 1. So of course there's a similar statement for in 3 dimensions. Then you have a function L3 of R3 with normalized to have 3-dimensional norm 1. So you can find now 3 functions. So this is Loomis-Whitney in 3 dimensions. So you can it's a cube root of the product. So again, the geometric mean of the 3 functions. That's a cubed root of the product. And you can sort of factor m into this cubed root. And so if you integrate the function s with respect to z, then for any x and y this is less than 1, and so on. For you integrate t with respect to y, then for every x and z this is less than 1, and the same for u. So we can sort of split somehow this function m into these very nice functions there. And there is this one other Braskamp-Lieb type inequality which has its applications in the convex analysis. I mean, this is a geometric Braskamp-Lieb of Ball and Barth in the general case, where you have, so again it's the same situation as we had. So Yj are subspaces of X and Bj's are projections, but additionally I'm assuming that I can decompose the identity operator on the big space Rn, or maybe I should have had X here. I can decompose the identity operator on this big space as this linear combination of these projection operator. So Bj is a projection, and Bj star just does nothing except it moves it's the inclusion into the space. So into the big space again. So so if this equality, if this decomposition is true, then the Prescott-Libby inequality is actually true with constant 1 here. And so, yeah, so I already said this, right? Okay. And then we get that these factorization theorems are, we can factorize M into this product with this weighted geometric mean of Sj's, and for any of the j's, if you integrate over the perpendicular set, you take a point and you integrate over the perpendicular space of yj at that point, then for every x in the yj, this will be less than this number here. So the constant is 1. So. And I just want to remark that if the dimension of, so the maybe original case studied by Paul, when these projections are all rank 1 projections, so the dimension of the resulting space is just 1, then actually this condition just means that the R is equal to n, which is the dimension of the space X. Okay. So just a couple of words about the general case. So for the general case, I mean, there are sort of a little bit of a functional analysis going on. The thing is that Lagrange multipliers are not very suitable somehow. I mean, you want to just have maybe make it a bit nicer. So what you do is you just test the. So this is one of the constraints, and you test this against the positive function g, and if you allow g to be any positive function, and then if you want this L to stay away from negative infinity, so you do the same stuff. You try and figure out how. I mean, there's you write down this expression, and then there's sort of two sides of the problem. You want to see that first of all, considering this for any g and for any h, then you have to have this inequality to hold to be in the interesting case, and also this inequality. So so this stuff here, if this inequality does not hold, then this expression will be positive somewhere. So if you allow g to be positive, then you can just throw this up to infinity, which is not the interesting case in this case. So you have to have, to be in the interesting case, you would have to have this condition to hold. And sort of the other condition, which we have here, we've sort of rewritten it using just the regular duality as testing it. So we have here the pj primed norm, but we are testing it against a function in pj. So we have just by the regular Hölder's inequality that this expression here is bounded by this stuff here, and then we compare this expression to this expression, and we of course have hj norms, pj norm of hj on each side, and actually it turns out then the interesting case will be this thing here. So just a little bit of flavor about how you sort of take this expression. You first of all try and calculate the soup with respect to the g and hj variables, and then you see that the interesting cases will actually be where this condition and this condition holds, and then conversely you look at the inf with respect to the sj and the k variables, and you get something out of that, and you can it's just sort of maybe a bit technical. And you notice that this is a function is actually convex in the k and sj variables, so it's linear here, linear, and this function, the weighted geometric mean is concave, but it has a negative sign, so it's convex. So g is positive, so it's convex, and it's concave in the other variables. So this is linear, and k is positive now. So the norm is convex, but it has a negative sign, so it's concave. So this is a concave convex function, And what we really are interested in, the result hinges on this this equality here, that we want to be able to interchange an inf and a sup. So of course one of these, this equality you can think of as two inequalities. One of them is very simple, that's somehow the weak duality, but then the strong duality, from if you think about it in terms of that, is a little bit more difficult, and you look at trying to look at minimax theory from functional analysis, find some minimax theorems from functional analysis, sort of the most standard ones, Kifan or something like this, they don't apply it directly because the domains of these functions are not compact spaces. I mean, K, for lots of things that I have talked about, then I have to send things off to infinity. I mean, it's not the interesting cases somehow, but they need to be there. So the domains are not compact spaces. So you have to dig up some better references. There are some theorems. There's a Vietnamese mathematician called Huan Thuy, who has some theorems which you can use and so on. Okay. And